stable. Notice we have a different number of nodes. I got 1, 2, 3, 4 nodes, whereas before I had 3 nodes, and I've got 3 antinodes. These are known as harmonics. This is the third harmonic.
Wait, what's the third harmonic?
The first harmonic is the simplest pattern you can get.
Okay.
Let's see if I can actually.
So that's
That's close to the first harmonic right there.
okay.
Where I have 1 antinode in the middle and I have 2 nodes on the outside. That's the first harmonic. Second harmonic for what's called 2 fixed ends. It's still not ideal, but. As I increase tension in the string, that starts moving. Coordination issues. Oh, there we go. Because increasing tension from the first harmonic doesn't help. If I lessen it, notice that there's sort of a second harmonic. I can't hold the tension steady. And then as I put less and less tension on the string, I'm lifting the string right now, you can start to see more places where there might be nodes or antinodes. However, we can see much more visual demonstration if we step out into the hallway. So let's step out in the hallway. Excuse me. I need a volunteer. Basically get this in. So right now, just hold that in. All right, so I send a wave down. What happens? Okay, so it reflects. What are you talking about the reflection? Yes. So when it hits a fixed boundary, it flips to the other side. So we didn't see it before this time. When it's send a wave on this side, it will return on this side. So that is a fixed end. Now put the rod through this direction to that fixed end. And then put the pull down in the middle and then pull on the outer parts of the rod. And no, nothing else. So now the end moves, that's a free end. So look what happens when it hits the free end. How does it reflect? On the same side, yes. So for a free end, it will reflect on the same side, fixed end will reflect on the other. that recorded the blank board there. Yeah, that was going. So what we were demonstrating out there is known as a transverse wave. Because the signal that was being sent, or the wave that was being sent, was going from me to Rayan and back. So the wave was traveling this way in the hallway, but the coil itself, the particles in the coil, or each coil, was traveling this way. So a transverse wave, the wave is perpendicular to particle movement. So the stadium wave is an example of a transverse wave.
Say that one more time?
The stadium wave?
Oh,
Yeah.
okay,
Because the particles, the people, are moving up and down, but the wave is traveling
okay.
parallel to the seats.
Okay.
That's a transverse wave.
Okay.
Longitudinal wave is the other major type. Longitudinal. And the particles move parallel or anti-parallel to the wave. And sound is an example of that. So when I produce a voice, my vocal cords are vibrating back and forth. They're pushing air molecules against other air molecules, which hit other air molecules, and so forth. What is hitting your ear is not particles coming from my voice, but a particle that got hit by another particle, got hit by another particle, got hit by another particle. Unlike the transverse wave, where it was being pulled. So as one particle moved this way, it pulled the next part of the coil with it. So the wave is parallel or anti-parallel to particle movement. These are the two major types of mechanical waves, as opposed to electromagnetic waves, which is a 152 topic. So what's happening here is it sends a wave down, the wave reflects, it interferes with the next wave coming down, and if you get the right frequency and tension, that it will start to create patterns. Now in both cases, if I'm sending a wave, what affects how fast it's going is one, how much mass am I trying to move? The more mass I need to move, the slower the wave's going to be. And the other thing is, how much does one particle's movement affect the other particle? So we have a generic relationship for the speed of a wave through a medium. There's some force term. This is, if I move this particle, how much force will it apply to the next particle? So in the coil, as I move one coil, how much does it affect the next coil? And the greater that force is, the faster the wave will move. Over the inertial term, this is where mass would show up. Now specifically for something traveling along a wave, traveling along a string, so specific to the one-dimensional motion, the tension divided by the linear density. Mass divided by length.
So the linear density is mass divided by length?
Yes.
Okay.
Regular density is mass divided by volume. Linear density is mass divided by length. Now, if you want to make an argument that there's no such thing as a one-dimensional object, that string is three-dimensional, just two of the dimensions are really skinny, you could do a far more complex formula, but it ultimately would reduce down to really close to this. This is good enough if the two of the dimensions are incredibly tiny compared to the length. No, I'm not gonna shoot this. Come on, hook. So let's make a prediction. All right, so let's see if we can get a harmonic in here. All right, that looks rather stable right there. I think we clearly have a node here, here, and here. A little less stable as I start wiggling it around. All right, somewhat stable right there. They are hanging freely, although they're really close to touching the table there. All right, so this is the second harmonic. So the thing was vibrating at 88.4 hertz. So my frequency, 88.4 hertz, which means that thing was vibrating up and down 88.4 times a second. The speed of the wave is, well, let's hit wavelength. So we got frequency, we can figure out the wavelength.
You said
That was, pardon?
Sorry, you said the 88.4 was what?
The frequency.
Per second.
So it's, a hertz is cycles per second. So this thing was vibrating up and down 88.4 times every second.
Okay.
As you could clearly see if you counted the number of times in a second.
And you got that number from your machine?
Yeah.
Like it tells you?
I got it from
You
there.
didn't have to calculate it?
Correct, correct. So our first harmonic is the simplest wave pattern like that. Second harmonic, which is what we were seeing right there. This is for two fixed ends. First harmonic, second harmonic, and so on. You add a half wave every time. Well, a full wave, basically, if you think about a sine wave from 0 to 2 pi, it looks like that. We represent it like a standing wave. That's one wave right there. So how many waves is this?
Half.
Yeah. So this is half of a wavelength. How many wavelengths is this?
One. So the lambda is.
The symbol for wavelength.
Okay.
So since this was a second harmonic, and that's the equivalent of one wavelength, I can just measure that length there. And I have the wavelength. And it's looking like 92 centimeters. So in this particular case, 92 centimeters, which is 0.92 meters. What's the formula for speed? Average speed. Flashback to chapter 2.
Initial speed plus final speed divided by 2?
Only if acceleration is constant. okay, that's velocity, but speed, distance over time. Classic middle school formula, gotten already. Distance divided by time. So I have this wave traveling down there, and the time it takes to go up and down, basically, the wavelength is how far it travels in the time it takes to go up and down. In other words, the wavelength is the distance traveled in one period. So flashback to the last Thursday. I know we've done this at some point last week. The period is the number of seconds to create a cycle. Frequency is the number of cycles I do per second, or per some unit of time. So whatever the period is the same as the frequency. So I have lambda times 1 over t, which is just lambda times the frequency. So for anything that is in cyclical, any wave in cyclical motion, or any wave that's anything oscillating back and forth, creating a wave, the speed of the wave is equal to the wavelength times the frequency. So I can find the speed of the wave is lambda, so 0.92 meters times the frequency, 88.4 hertz. And so what was the speed of the wave using this formula? Say it again.
81.33.
Units?
Meters per second?
Yes.
No, I thought.
A hertz is a cycle per second, and it's metered, and so you have meters per cycle times cycles per second, meters per second. So that is the prediction. The tension in the rope, if this is an equilibrium here, so if this is an equilibrium, I know the tension in the string here must be equal to the weight. So if I trust the manufacturer, which I will for the moment,